Hello, beautiful humans. Bear with me one moment. Here we go. We are going to be talking about linear inequalities today. So remember, inequality means just not equal. So unlike in the past where we've talked about equations, right? So a linear equation means that we have points that are on the line. Those are going to be our solutions. A linear inequality is going to have actually even more possible solutions because it means not equal. So you could be greater than the line or less than the line or greater than or equal to or less than or equal to. So that's what we're going to be talking about today. So again, a linear inequality is just like an equation, except instead of using an equal sign, we're going to use something like this, an inequality symbol. Okay, and that represents that all the values, there are going to be even more solutions. They can be above the line, below the line, on the line. I mean, there's not technically more solutions because remember, there are infinitely many points on the line, but there's a greater region of solutions with inequalities. We call the area that holds the solutions the feasible region. Feasible meaning possible. So when you think about possible solutions, they are found in the feasible region where these solutions can live. So when we graph these and shade them, the shaded region holds all the answers and is called the feasible region. Okay, so how do we do this? Well, the first thing you want to do is rearrange your inequality so that y is all by itself, so it's isolated, because it's easiest to graph a line when it's in slope-intercept form. So we're going to rearrange everything, moving our y so that it's all by itself and graph from there. Then you graph it just as if it were a line, except you have to pay attention to these symbols here. Because if you have greater than or equal to, your line will be solid. But if your inequality symbol is just less than or just greater than, then you're going to have to use a dashed or a dotted line to indicate that the line is not part of the solution. So if y must be greater than the line, then it can't be on the line because that's not greater than the line. So those inequality symbols do matter. We use a solid line when it's greater than or equal to or less than or equal to, and we use a dashed or dotted line for when it's just less than or just greater than. All right, so one variable inequalities, we're going to graph those on a number line. Whoop, let's actually get a pen here. Number line. Okay, so that would be something like x is greater than 3. Well, if you graphed x is greater than 3 on a number line, you'd go to your number line, you'd put 3 in the middle because it's the most important, and we'd use an open circle. So this is going to be an open circle. Right? And then x is greater than, values that are greater than would be like 4 and 5. So that's the area we're going to shade that direction, right? Okay, what about less than or equal to or greater than or equal? So what would be the difference if instead I said x is greater than or equal to 3? Well, now at 3, we're going to have a filled in, indicating that 3 is a part of the solution. 3 is would make the statement true. 3 is greater than or equal to 3 because it's equal to 3. And then again, values that are greater than would also be shaded to the right. So again, if you have one variable, just an x all by itself, then you're going to graph this on a number line. We use open circles for greater than or less than. We use closed circles for greater than or equal to or less than or equal to. Two variable inequalities would be something like y is greater than x plus 2, right? So that is I see two variables there. I see an x and a y. We graph those in the coordinate plane, right? So on a graph, like in the grid, right? The coordinate plane. So that's going to look like that. If we have greater than or less than only, so I'm just going to graph this line. I have a y-intercept of 2 and a slope of 1, up 1 over 1. This is my approximate. This would have a dashed line, again, because it's just greater than, not or equal to. And because y is greater than, this is going to shade above. We're going to talk about all of this in a minute. We'll test a point to be sure, but again, I've practiced this a lot, so I'm pretty sure. All right, if, however, it was y is greater than or equal to x plus 2, well, now in the coordinate plane, we're going to use a solid line to indicate that the line is a part of the solution. So now when we graph it, the difference here is points on the line are also going to give us a true statement. So the line is going to be included in our solution set. Again, this shaded region here we call the feasible region, where the answers lie, the solutions. If I were to pick a point up here, like, I don't know, -3, 5, that value when plugged into your inequality would make a true statement. So let's try it. 5 is greater than -3 plus 2. 5 is greater than -1. Yup, that's a true statement. So again, all values that are true will give you, or all values in the feasible region will give you a true statement if you were to test them, which also means that if you were to test something not in the feasible region, you would get a false statement. All right, so let's try this out. We need to graph these. What do we need to pay attention to? Well, we need to pay attention to the fact that this is less than or equal to, so this will be a solid line when I graph it. I'm going to start by graphing my y-intercept of -2, down 2, and I'm going to put my point. My slope is 2/3, so I'm going to rise 2, up 2, and run 3. 1, 2, and 3, and that's my new point. Again, this is going to be a solid line, so I'm just going to draw my line through those points. And then we need to determine where the feasible region is, and we need to then check or identify 3 solutions, and we need to check one of them. Okay, y is less than. The values are less than the line, so I assume that will graph down here. Again, I'm doing a guess right now. I'm going to test a value that is down there, like easy one would be 0, -5 or something, right? So 0, -5, I believe is going to be in my feasible region. So when we test it, it should be true. We only have to test one point because all the points in that region hold the same fate. They are either all true or they are all false. So if you test one point, you have effectively tested all of them, as long as you're being careful with your work. So we're going to plug in -5 for y. -5 is less than or equal to 2/3 times 0. Again, pick friendly points to make your life easier when you're testing. -2. Well, this just cancels out, and we get -5 is less than or equal to -2. That is a true statement because -5 is in fact less than or equal to 2. Actually, this whole thing should be moved down here because that's that check step there. Okay, but up here, so what's another value over here? Well, we could use literally any points down here. Any of these purple points would be true. So you can list any of them. So we could do, I don't know, 10, 0. That would be in my feasible region. We could do 2, -10. That would be in my feasible region. We could do 0, -20. That would be in my feasible region, and so on and so forth. Okay, you give this next one a try. All right, we're going to start by plotting our y-intercept of 3, 1, 2, and 3. Plot my point. And then my slope is -2, so I'm going to go down 2 and to the right 1. Again, one of your directions needs to be negative. We could also go up 2 and to the left 1. That would be the same. Now, look carefully. This is just less than, meaning this line needs to be dashed or dotted. It is not a solid line because it is not a part of the solution. So this point right here, this y-intercept of 0, 3 would not give us a true statement. It is definitely not in the feasible region because this line is dashed, meaning no points on the line will satisfy our inequality. Okay, again, y is less than, so I'm thinking of values of y that are going to be smaller below this line. But again, of course, we're going to test. I'm assuming 0, 0 is in there, and 0, 0 is a really nice number or really nice point to test because it's super friendly. 0 is less than -2 times 0 plus 3. Well, 0 is less than 3. That's a true statement. So I have identified my feasible region, which is right here. So everything below this line is my feasible region. So any point there will give us a true statement. 0, 0, -5, 0, -2, -25, right? Anything over there, you could come up with infinitely many points, definitely not points on that line, however. Okay, when you have just a y equals line, remember if you had y equals -4, that would just be a horizontal line at y equals -4. So remember, y equals lines are horizontal lines. So y all by itself as an inequality is going to be a completely horizontal line. But again, now we have to pay attention to whether it's dashed or solid. So at -4, we're going to put a point 1, 2, 3, and 4 because that is our y-intercept. And then we get to do a solid line here because it's or equal to. So a solid line. Again, in this case, y is less than, so I expect to shade down here. I'm just going to test an easy point like 0, -5. So I think 0, -5 should work. So let's test it. -5 is less than or equal to -4. We don't even have an x to plug in, so we don't need that 0 at all. And that is, in fact, true. So what else would work? -2, -5, 25, -7, right? As long as your y value is less than -4 or equal to, so we could also have anything on the line would work this time because the line is a part of our solution. So any of the points on that line would also work. All right, you try this next one. Remember, if you have just a plain old x equals line, that's going to be a vertical line. All right, so we have x is greater than 6. Remember, greater than, no, or equal to. So this is going to be a dashed line. It's going to be a vertical line at 1, 2, 3, 4, 5, x equals 6, right? But again, we're going to do a dashed line to indicate that the line is not a part of our solution set. It is not included in the solution set. And then we're looking for values of x that are greater than 6. So values of x that are greater than 6 are going to be in that direction, right? The positive direction. So what do I think might work? 6, 0. Oh, no, not 6. Sorry, greater than 6. Try again, Fennell. I don't think 6, 0 will work. I think 7, 0 will work. I think 25, -50. Whoop. Will work. Again, anything over here, right? We can go down infinitely. We can go up infinitely. It doesn't matter what y is, as long as your x value is greater than 6. So again, any x value greater than 6, 9, 0, or anything else, right? Let's test one of them. Let's just test one of the zeros. It's easier. 7 is greater than 6. That's a true statement. We have shaded the correct region. We are good to go. Notice if you were to plug in 6, you would get a false statement. 6 is not greater than 6. That symbol indicating, again, only values greater than will be true. All right, here we go again. I see just less than, so I want to make sure that, oh, I'm missing my graph on this one. Okay, we'll just rough graph it over here. Just less than, so I assume that, or 1, 2, 3, 4, and 5, there's my y-intercept. I'm going to go up 2 over 1, positive slope there, and a dashed line. Again, a dashed line because we are not or equal to, we are simply less than. Again, less than values I would assume are down here, but we are of course going to test. I would assume 0, 0 would work. I would assume -1, 0 would work. 5, 5 should work. Again, you could any points in the feasible region, any points in the shaded region should work. Let's test one and be sure. 0 is less than 2 times 0. Again, pick the friendliest point you can to test. 0 is less than 5. That is a true statement, just like we expected it to be. Good to go. All right. Over here, give this one a shot. We have -4 is our y-intercept. 1, 2, 3, and 4. Plot that. Our slope is negative. Careful, it's hiding there. A -1 over 3. So I'm going to go down 1 to the right 3. Or we could go up 1 to the left 3. That would work as well. Because we are greater than or equal to, I'm going to put a solid line there because it's or equal to, meaning the line is a part of the solution set. In this case, y is greater than, so I want bigger values. I assume that's going to be up here. Again, 0, 0 appears to be in that region. That's my favorite point to test because it's easy peasy. We could also do -1, 0, or 25, 0, or, I don't know, 2, -2, right? Tons of options. Anything in this feasible shaded region here will do the trick. Again, I'm going to test 0, 0 because it's the easiest. 0 is greater than or equal to -1/3, times 0 minus 4. 0 is greater than or equal to -4. That is a true statement. You would rather have $0 than owe someone $4. True, true. All right, hopefully that makes sense and you get the general idea of this. Have a wonderful rest of your day.